So good morning, everyone. Welcome to the Good Vibration Seminars. So today we have the pleasure to have Björn Muller for our fifth seminar of the season. So actually it's fifth because it was supposed to be in December, but then it was moved. So Björn Muller is a PhD student at the Max Planck Institute for Solar System Research in Göttingen. His research interests are helioseismology and inverse problem in astronomy in general. So for his bachelor, which he's completed in the Georg August University of Göttingen, Björn has followed a double curriculum of physics and mathematics at the same time. He started working on the sun with the researchers of the Max Planck for solar system research for his bachelor. His bachelor thesis subject was inversion of meridional flow using Pinsker estimator. And then for his master's, he turned to extragalactic studies and conducted a master thesis about reverberation mapping of active galactic nuclei. But something tells me that it's not completely unrelated to the techniques he used before. He then went back to helioseismology and to the MPI for solar system research for his PhD that he started 3 years ago under the supervision of Laurent Gison and Thorsten Hoheit, I'm sorry for the pronunciation, and Damien Fournier. So a double supervision by a mathematician and a solar physicist. And the subject of his PhD is iterative helioseismic holography, sorry. He should complete it later this year during fall, and he will be looking for postdocs then. So today he will talk about part of his PhD work. His talk is entitled Imaging Subsurface Solar Flows by Iterative Helioseismic Holography. So thank you very much, Björn, and the floor is yours.
Yes, thanks for the introduction. So I'm planning to speak about imaging of subsurface solar flows by iterative helioseismic holography. This is the central part of my PhD thesis. But I also want to spend some time to speak about quantitative passive imaging problems in helioseismology, which is like the other part of my PhD thesis, but maybe does not fit so well to the Good Vibration seminar, but I just want to spend some time on this. So my PhD is supervised mainly by Thorsten Hoheit. He's a mathematician here at the University of Göttingen, and by Laurent Gison and Damien Fournier. Okay, let me first start with introducing you the passive imaging inverse problem in helioseismology. So I'm studying acoustic modes, and for acoustic modes can be described by a scalar Helmholtz-like equation. Looks like this, with a k wave number, which is strongly dependent on values. We have the density rho, the sound speed c, u flow fields. So in particular, I'm interested in large-scale flow fields like differential rotation and meridional flows, but maybe after my PhD we are also interested in supergranular flows, which will be a more complicated problem to solve with iterative helioseismic holography. The reasons for this I will present later on. So we have some stochastic source term S, and finally we have to set boundary condition in order to have uniqueness here, and we use this atmospheric boundary conditions. There are other boundary conditions, but for our purpose this will be enough. So our data we have are Dopplergrams. So here you can see a Dopplergram with the color scheme from left to right coming from differential rotation. And yes, so what we basically observe are the line of sight velocities. So the line of sight velocities are not exactly the scaled wave field we have in the equation here, but it's in some kind proportional, at least for modes which have small enough L. So let's take this assumption that we could directly measure our scaled wave width psi. And then in order to define our passive imaging problem, so the difference between a passive imaging problem and an active imaging problem is that in an active imaging problem, we know the sources. But in a passive imaging problem, the sources are stochastic and we only know some distribution about the sources. So the passive problem is harder than the active problem. And here we assume this relation for the source strengths. So we have spatially uncorrelated sources, and there are also now cross terms between different frequencies. Our input data consists of cross correlations between two different points of the solar surface at one frequency. So it can be written down in this form. So and overall, I think all of you know this. So the aim of helioseismology is that we want to study the solar interior from measurements of solar oscillations on the solar surface. Now we have the problem that our input data set is very, very big. So if we just look at the correlation data as our input data set, it is 5-dimensional. So we have 2 dimensions for R1, 2 dimensions for R2, and 1 dimension for the frequency omega. And further on, it's extremely noisy due to the realization noise. So in inverse problems, in general, realization noise is often much harder than just Gaussian white noise. But on this slide, I want to focus on the pure size of the input data set. So if we have data on a CCD grid with 4K times 4K points. So this leads to roughly 10 to the 13 cross correlations, independent cross correlations, and this is for each frequency. So the number of frequencies available is linked to observation times. If we have, for example, 4 days of observation, we come out with roughly 5,000 frequencies. So at the end, in my inversions, I will use less frequencies because you have to do also some filtering and so on. But we have to multiply this number with our number of cross correlations. So 5,000 times 10 to the 13. And we see it's even, we can't invert this directly by standard inversion methods. And even to store this can become complicated. So we need to do some averaging in spatial domain and also in frequency domain. And this is one way to understand time-distance helioseismology. So if you look at the image here, this is some part of the cross correlation averaged over angular distance. And in time-distance helioseismology, we are only interested in the time shift tau between a reference model and the measured model. But so from this plot, we only take like one quantity and forget about the shape and the amplitudes and so on, which will be informations which are in the total cross correlation. So the goal of my thesis is I want to use the whole correlation, the whole seismic information, and hopefully if we use the whole seismic information, we can improve the inversion results. So the traditional approach of time-distance helioseismology is that we measure travel times between 2 points, A and B, at the solar surface. So I have point A and is traveling to point B. So every ray path here corresponds to exactly 1 point in this diagram. So usually travel times are affected by local perturbations on the ray path. In particular, they are affected by, for example, flow fields. So, and this leads to an inversion problem, which is, for most cases, we can assume this to be a linear inversion problem, so that the first Born approximation holds. And the way to understand this, I said it before, so in time-distance helioseismology, we use the high-dimensional correlation data, and we reduce this data set to maybe 10,000 travel time measurements. And from this, we get a kernel equation and can invert for our quantity here for the flow fields, for example. But this has some limitations. So it was shown that the reduction to travel times lose some information. So, and the question is how much we lose. And further on, there is some work on extending time-distance helioseismology also to nonlinear problems. And if we are interested in differential rotation, for example, so a DC perturbations through the cross correlation is nonlinear and can't be tackled by just linear equations anymore. But it's not really done or not really common up to now in the helioseismology community. So, and the reason is that these sensitivity gradients K are very hard to compute. They are just computationally very expensive. And so in most cases, we are dealing just with linear inversions in helioseismology, in particular in time-distance helioseismology. So, but there's another technique called helioseismic holography. And the idea is, first here on the left side, in the image you see like the forward problem. So you have some seismic sources. It's not totally correct because in the sun you have more like extended sources and not discrete sources. But let's assume we have some seismic sources here, then the waves are propagating to the solar surface. And here we have our surface disturbances, which are our measurements, basically. And now in holography, we take our surface disturbances as seismic sources and go back in time. Back in time, for this we need some backpropagator, H alpha and H beta, which are basically adjoint of Green's functions. So that they are really directed back in time. And now we often in helioseismic holography is, so if we have the sampling surface on the same point as the or on the same height as the original seismic sources, we get very sharp images and it blurred out if we are out of target. So we can make use of this, but it's also some kind of a problem because again, we have to take the cross correlations on the whole surface and then backpropagate them. So this is written down here. So here you have the cross correlations and your backpropagators H alpha and H beta star. And now you can just make a change of order. So you take out the summation out of the integrals, and then you have an you compute the holograms, two holograms here and here in the brackets. And just by changing the order, we use the whole cross correlation data implicitly because it's the same formula. But there is no need anymore to really compute this quantity. So it's a big advantage, and we want to use this in our inverse problems, in our iterative setup for inverse problems. Let me summarize it. So in time-distance helioseismology, we start with our Dopplergrams, psi I. We compute the cross correlations. From these cross correlations, we compute travel times, and then we do an inversion. In helioseismic holography, we start with the same data sets, our Dopplergrams, but first backpropagate them to holograms and then locally correlate. So here we change the order, and in this way, as I said before, we use the whole cross-correlation data, but never compute it and have to store it. So it's a big advantage. But unfortunately, helioseismic holography, and in particular here, I've done it for Lindsay Brown holography in a two-dimensional uniform medium. As a toy example, it is not a quantitative imaging method. So if you look at these examples here for a sound speed of 200 kilometers per second and wave number given by this formula at 3 millihertz, you see that, yeah, for small damping rates, the features are mainly visible, but they are not visible anymore if you have big damping rates. And furthermore, the scale is totally wrong. So we have to do some work in order to use this helioseismic holography backpropagating trick we want to use because we don't want to compute the total input data set, and we have to turn this into a quantitative imaging method. And now it becomes a little bit more mathematically, but in order to do this, we have to define a covariance operator. First, G will denote the Green's function here, and the volume potential operator is defined by this formula. Furthermore, we have to define a multiplication operator. This multiplication operator will be used to describe the source strengths, because we have assumed spatially uncorrelated sources. It can be written down by this. I've proved in parts of my PhD thesis that the multiplication operator really is a Hilbert-Schmidt operator. So it makes sense. Hilbert-Schmidt means that the kernel is A2 integrable. So there exists an adjoint of this, so it's technically interesting that we have this. And finally, we have the trace operator, which is just the evaluation on the solar surface. So overall, we can write down the covariance operator in this way. This is our volume potential operators here. And now if you look at the Schwarz kernel or the A2 kernel of this, it's what you know from helioseismology. So this is the connection between helioseismology and more the inverse problems community. From this we can compute the Fauché derivative. If you work a little bit on this, you will see that it looks like this, and the adjoint takes this form. And now I've marked some things here. So the first things, these operators will become our backpropagators. So backpropagator H alpha and backpropagator H beta star. And this one is a local correlation operator. So if DFLF is just like a multiplication, then it's again taking just the diagonal of this. So for the first time, it looks maybe a little bit strange, but it's really what you have before if you go to this formula. Okay, what we see, again, let me state the forward problem and the inverse problem. So the forward problem is that we have a solar model defined by density, sound speed, flow field, and damping rate. And we compute the cross covariance at the solar surface. And the inverse problem is the other way around. So we want to reconstruct one parameter of interest. So maybe also two parameters at the same time from observations of the cross correlation of the solar surface. What I wanted to show you before is that the hologram intensity is nothing else than the adjoint of Fauché derivative of our correlation data set once we fix the backpropagators H alpha and H beta. So it's some kind different way to go. So before we had we fixed our backpropagators in holography just by clever choices in terms of signal to noise ratio, and now the propagators are fixed by the forward differential equation, and we try to improve just by iterating over it. So once we have it in this way, we can start a usual Gauss-Newton algorithm in order to solve this nonlinear inverse problem. And so in each iteration, we have to solve this normal equation. So, and if we go back to our notations we have in holography, so the left side is just the expectation value of the variation of hologram intensity. So this becomes the hologram intensity, and this becomes the expected hologram intensity. So the holographic image is the first step of a Gauss-Newton algorithm for solving nonlinear inverse problems. So, and if we have this, we can just start iterating over it. I started with two challenges at the beginning. The one was that we have a large input data set. So this is now solved by using this holographic backpropagation trick. And then that we want to solve also nonlinear inversions. And yes, this is now solved by starting a Gauss-Newton algorithm here. So let me shortly show you the algorithm. So the crucial part is to compute the Green's function in each step. Once we set up the stiffness matrix, it's pretty easy to compute the propagators and to compute the adjoint and derivatives and so on. Once we have the propagators, we can compute the holographic image and the forward kernel. And finally, we have to solve this normal equation with some sensitivity coordinates k, alpha, beta. This will be done by, so usually these operators are 3D to 3D operators, so it's not a good idea to store them. But for meridional flows or different rotation, it will be possible. And we solve this equation by an inner conjugate gradient method. So there are some problems. So we have very large computational costs for the computation of Green's matrix, of Green's function. And yes, I want to show this later on. So first we started with some toy examples in 2D uniform medium. Why 2D uniform medium? Because in a 2D uniform medium, it's still possible to do the inversions without thinking about the computational cost so much. So I started with some surface inversions. This is a linear problem, and the Green's function is unchanged in each iteration. So it's the most simple problem we can work on. You see this in these two images, and it's very good. It's already done with only part that we assume that we have only information on parts of the surface and with strong realization noise terms. So for source length, we don't have a problem. For sound speed density and damping, it's a nonlinear problem, so we have to solve the Green's function in each iteration, but also then with strong noise terms already, it seems to work. And finally, we also tried flow fields. For flow fields, we have to say that we have to incorporate mass conservation constraint in the inversions. Yes, but also in iNorm, it looks really good. So we are really happy with this. And now try to go to realistic sum problems. For realistic sum problems, we have the problem that we have to deal with the immense computational costs. So let's do a simplification. There are no flows, which means that our equation just looks like this. And now if you look at this potential k squared at 3 millihertz, you see it has some kind of a strange behavior. So look, it's very close to the surface here. And in order to model this, we need a very fine finite element grid. For example, here, so it becomes very fine close to the solar surface, and therefore we have a lot of degrees of freedom. So I have done it here for 1D and 2D. Basically, you can also 3D, but we don't really have a 3D solver. So the degrees of freedom for 1D are 10 to the 3, roughly. It's very fast, far less than 1 second to compute this. But for 2D, we have already 10 to the 6 degrees of freedom, and it takes roughly 2 minutes to compute them. And then you have to multiply this with the number of frequencies you have and the number of modes you have. So even after parallelizing our frequencies and modes, it's a big problem. So this is the reason why we started to look at large-scale flows like meridional flows and differential rotation, because there are some tricks that you can decrease the computational costs. For example, you have sparseness of coupling coefficients. You can use Clebsch-Gordon coefficients and some preconditioners, but I left this out for this talk here. That's the reason why we, at the moment, not studying, for example, supergranular flows, because there we really have to solve these problems, and this will increase the computational costs again. So finally, let me come to numerical results on solar differential rotation. The traditional approach is to measure the solar differential rotation by frequency splitting. So this leads to again a kernel equation which can be solved for the rotation at omega. Here you can see a exemplary rotation profile for the sun, but these kernels have a lot of symmetry relations, and one of the relations says that we have no sensitivity to the antisymmetric part of, so to the part different in northern and southern hemisphere of the solar rotation. And in principle, we can do this with holography. So this is a motivation to use holography for studying solar differential rotation. So I started with decomposing the solar differential rotation in Legendre polynomials, and this already looks fine. Here it's only going to a number L equals 10 as maximal number, and it's already a good decomposition, I think. So the back propagators are fixed by the forward differential equation, and now we have some problems. The problems is that we have so immense computational costs that we, even with parallelization in frequency and azimuth order, it's a big problem, but our correlation coefficients are very sparse if we work in spherical harmonic basic settings. So I've done it here for differential rotation and meridional flows. And you see, so every second coefficient is 0 just because of symmetry. But also if you go very far to the right side, very far on the left side, you will see that they are really, kind of vanishing. So it becomes sparse. And we have the advantage that we can solve the integrals in angular direction analytically. So it's like we have a 1.5D code to compute the forward problem. So it turns out that we have to do some likelihood modeling. So we have to incorporate in our inversions also the cross correlation data of cross correlations, which are basically fourth order correlations. This can be seen by Iseli's theorem. And furthermore, we have leakage. Leakage means that we only see roughly 1/3 of the sun. So spherical harmonics are not orthonormal anymore. And this again increases computational costs. Here we have computed the signal to noise ratio, so it's very strongly oscillating, which is the motivation to really average our frequencies. But one important part is, so if you take the running mean of the signal to noise ratio, it seems like it is increasing to smaller frequencies. So here I've computed the sensitivity kernels defined by this equation. And the radial resolution is very close to half of local wavelength, which is a lower resolution limit. So we are really happy with this, and I think in this kind, holography outperforms time-distance helioseismology. Then we have this ghost on the other hemisphere, and furthermore, there are always strong terms on the solar surface. This comes from the strong gradients you have in the strong sound speed and density drop there. Let us have a look at the averaging kernels, and again the radial resolution is close to half of the local wavelengths, and we are really happy that we successfully can reduce the surface terms. So if you look at the averaging kernels here, they are not so dominant at the surface anymore as the sensitivity kernels I showed before. Finally, the inversion results on synthetics. So starting with noiseless inversions. So there it works, and it even works for modes above the acoustic cutoff frequency. But yeah, for terms with noise, this will be not the case anymore. Then we have added 10 years of realistic noise. And always this blue curve is, because we have so many iterations and every iteration is so expensive, we start with a very, very easy differential rotation profile, which is always defined by this blue curve, only 4 points in the convection zone. And yes, this will be our initial guess, and we try to decrease the number of iterations by using this these algorithms. So, and we see that it's likelihood inversion. So if you look here, it's a little bit oscillating. So maybe we have to stop earlier. But with likelihood inversions, we have very good inversion results, whereas with A2 data fidelity, it becomes slightly worse. And if you now go to take into account also leakage, then just A2 data fidelity terms will not work anymore. And the result becomes worse, but it's still okay. And consider we have only taken a maximal L of 100. So for the sun, we have more data, and we can also work on bigger Ls here. And finally, noiseless inversion with leakage again works very well. So the question is, what can we do and what maybe we can't do? So I've started with the motivations that with holography we want to invert for the antisymmetric part. And again, on synthetics, this seems to work. So here I've shifted minus 30 degrees and 30 degrees are not the same rotation rate anymore, and we are able to invert for this. Can we reduce the observational time? It seems like that we can. So here you have this realistic noise coming from 1 year of data, 3 years of data, 11 years of data, and yes, so it's possible. And last question, are we able to invert also down to the solar core? Not really. So if we have noiseless inversion, okay, it works. So we are pretty fine. Also with frequencies above cutoff frequency again. But if we add small, even smaller noise terms, 10 years of data is already pretty much. Yeah, we can't go down to the solar core. So in my last minutes, I want to spend on the second part of my PhD thesis, which is much more mathematically. And this goes with uniqueness proofs of quantitative passive imaging problems in general, and in particular for helioseismology. So we are studying two different problems. The first problem is an inverse source problem. So we have this covariance operator I showed you before, which has the connection that the kernel of this covariance operator is what we know in helioseismology. And we ask if this uniquely determines our source terms. And the harder problem is parameter identification problems. So if again, our cross-covariance data uniquely determines Q. There is some work on this by Alexei Agaltsov and Thorsten Hoage, but they have some problems. So Alexei studied the, oh no, this is wrong. Alexei studied the second problem, Thorsten studied the first problem. But for example, they assumed full data, which is of course not true if you can only observe part of the sun. They left out advection terms. Here, Alexei only showed a local uniqueness result, and they always assume that you measure the imaginary part of the Green's function and not the cross correlation. So there's a relation that the cross covariance equals the imaginary part of Green's function, but it would be better if you can prove it for every source strength. So this proof relies on Kramer's conic relations, and this proof relies on analytic solutions in the exterior, but assumes spherical symmetry, so it's also not so fine. And finally, Thorsten's proof assumes constant coefficients, which of course is not true. So sound speed is not constant, for example, in the sun. And he used completeness of plane waves. So I'm also started to work on this. So for the inverse source problem, and yeah, I just want to show you very briefly without the proofs how the proof works. So we start with, so it's a linear problem. So we can just solve for CS equals 0 and try to prove that S equals 0. This will show uniqueness. And the main idea is that if CS is equals 0, this equation holds true for every U1 and U2, L2 of gamma, and gamma is our measurement region. Then we can bring our T and G to the other side, and we have mainly this equation. And so under some technical assumptions, we can prove a result like this with K wave number. And finally, there is a result using Kalaman estimates and CGO solutions that for two parameters, V1 and V2 in the set H, if we can find such two parameters, such that exponential E gamma x, that becomes exponential E gamma x. And so if we insert this, we see the Fourier transformation vanishes, so the function vanishes. So I can say that the inverse source problem is mainly solved, but with the parameter identification problems, we have problems. So the question again is, if we have cross-correlation data, does this uniquely determine our parameters in the solar sun, in the solar interior? And we can't really ignore this assumption that CS is equals imaginary part of Björn's function. So let's start with this, and we have to assume that we have measurements at two different heights on the full surface, and then we can follow that from CQ1 equals CQ2. The Green's function on the surface have to be the same. So if we have this, then we have the classical Calderon problem, which is quite well understood, which says us that the parameters are the same up to a gauge transformation. And now for the sun, we have conservation of mass, of course, and also the parameters have to be real. And therefore we can, in some kind, work around this gauge transformation. So we can prove that ρ1 is equal to ρ2, but for the other parameters we have problems. So here we have only equality if we assume that one of the parameters is fixed. And open question is if this is really the case, or if we just haven't found the best way to work on it. Yes, so let me come to my conclusion. So iterative holography extends helioseismology to nonlinear problems using the whole cross-correlation data. We have some encouraging numerical results for solar differential rotation and also for meridional flows, which are not shown in this talk. Real sun problems are still challenging due to immense computational costs, in particular in the case of leakage. And as an outlook, we also want to do the same thing on supergranules. We want to further on work on this uniqueness results. And finally, of course, application to real data. This is my last slide. So here I've computed, I'm really doing this, this is an image from yesterday. So hologram at 2 millihertz for 6 years of data in the period of from 2014 to 2019. So, and this is again the coefficient of your Legendre polynomial. You see, so in the initial guess is a symmetric profile. So the one and the one Legendre polynomial becomes to 0. So, and it looks like there is some offset at least, and also, I mean, this part is the one which corresponds to the antisymmetric part, and looks like there is something, but now I really have to do this. I have to do this for more than one frequency, and also have to work on systematics like center to limb effect and so on and so on. So it's just a motivation that I'm motivated to work on this. So with this, I thank you for your attention. I hope you enjoyed my talk.
Well, thank you very much, Björn. I see that some are clapping. So thank you for a very nice talk. Quite a complex problem, of course. So I wonder if we have questions already. I leave it a bit of time for people to digest and react. So, well, I will start with one quick question, one outlook question. So you say that then you want to tackle the super granules, right? I guess that these flows are a bit more complex than large-scale differential rotation. So what exactly do you have to change, or what is the first challenge if you want to tackle those?
So even for differential rotation, the main challenge was this computational costs. I mean, it took me like 6 months to set up a solver which is efficient enough to really do this. But for differential rotation, you have the trick that you can work in spherical harmonic spaces, and you have the sparseness of your couplings coefficients and so on. And this will not be true for supergranules anymore. So you really have to work on your finite element grid in each iteration for each mode, for each frequencies, and so on. And so it just takes longer to do this because you don't have these tricks, or I don't see them at the moment.
Okay, thank you. So do we have another question? I see that we have some experts in inversion techniques in the audience. Feel free to ask. Of course, it's a bit challenging to ask a question to a mathematician, but let's see. Okay, Björn, please do.
Well, thank you. This is very interesting. And of course, getting around the symmetry of standard inversion is really very important. So this is encouraging. I wonder whether you've started, two questions. Have you started the noise properties, and do you get a measure of the standard deviation of your inversion results? And you have tried to invert noisy data, so that gives some indication, but is there a way to get from the noise properties of the observations directly to the noise properties of the inversion result? That's one point. The second point, of course, that you have to ask yourself is, what about magnetic fields?
Yes, so to the first question, I didn't study this. So yes, I have done it with, I've done inversions with noise, with noisy data, but I haven't computed the standard deviation in your inversion results. This would be a nice test. And to the second equation, I just ignored magnetic fields. So hopefully this is for differential rotation and meridional flows not a big issue. But of course, if you go to, for example, sunspots or stuff like this, and maybe invert for sound speed inversion perturbations, they are not for flows, this will be a big issue. And where it comes in, we have to, in some kind, we should have to change the forward problem, the differential operator, and then also the back propagator will look different. So it is will be a different algorithm then.
But also you have the issue that you're working in terms of the amplitudes of the signal.
Yes.
And that amplitude is also affected by the presence of magnetic fields. We know that magnetic fields suppress the amplitude of the oscillations of the waves. So it sort of enters also in the crosstalk and the filtering.
Yes, so the way I'm working on it with data is that I'm matching. So if you look just at where the frequencies are, the power spectrums of the forward computation and the observation are really nice. And now I inserted a correction function so that the amplitudes of the power spectra are also very similar. And yes, the hope is that this will take out most of the errors.
Yeah, okay. Thank you.
Thank you. So anyone has another question? So I will ask my very stupid question. So you, in your algorithm, you start with a given solar model, and that defines your Q naught, I think. So I'm really not familiar with local seismology. So I was wondering, what is it exactly that you call solar model in that case?
So for my inversions, yeah, I started from scratch. So it's a spherical symmetric model, solar model S, and yes, so this is a background model, and once you have set it up in a first iteration, after this, it's changed for every iteration. So since I'm looking on differential rotation here in my talk, it's so sound speed profile, density profile, and so on will always be spherical symmetric.
Okay, thank you. Okay, well, if we don't have other questions, then I will thank you very much, Björn, for your very interesting presentation and answers. And I will invite you to come back in 2 weeks for the next Good Vibration seminar. So thank you, everyone, for being here with us today, and see you very soon.
Yes, thank you.